Greetings and welcome to Talk a Little, Learn a Lot, the American Society of Naval Engineers podcast. I am your host, Stephen Phillips. In this podcast, we talk a little and learn a lot about naval engineering while inspiring the next generation of STEM professionals. Today, I'm joined by Rear Admiral Peter Small, Chief Engineer and Naval Sea Systems Command Deputy Commander for Naval Systems Engineering and Commander, Naval Surface and Undersea Warfare Centers, to hear his perspective from a career in naval engineering. Rear Admiral Pete Small is a native of Tabernacle, New Jersey. He was commissioned from the Navy Reserve Officers Training Corps at the University of Virginia, where he earned a Bachelor of Science degree in mechanical engineering. He also has Naval Engineer and Master of Science degrees in mechanical engineering from MIT and a Master of Science in Operations Research from Columbia University. He is a professional engineer in Virginia. As a submarine officer, Small served aboard USS L. Mendel Rivers and then as assistant professor of naval science at the State University of New York Maritime College and Fordham University Naval ROTC. After a lateral transfer to the engineering duty officer community, Small served across all phases of ship and submarine design and construction. He oversaw Virginia-class submarine construction and Los Angeles-class submarine repair at Supervisor of Shipbuilding Newport News, Virginia, and later served as the program manager's representative for Virginia-class submarine construction at Subship Groton, Connecticut. In 2010, Rear Admiral Small was appointed Associate Professor of the Practice in Mechanical Engineering at the Department of MIT and taught ship and submarine design in the Graduate Naval Construction and Engineering curriculum. He continues to teach submarine design in the MIT Professional Summer Program. In NAVSEA headquarters in Washington, D.C., Small served in the Advanced Undersea Systems Program Office, Columbia-class Submarine Program Office, and AUKUS Nuclear-Powered Submarine Consultation Team. Rear Admiral Small served as the Major Program Manager of the Unmanned Maritime Systems Program and later stood up the New Attack Submarine Program, commonly known as SSN-X. In 2024, he was promoted to flag rank and assigned Chief Engineer and Deputy Commander for Naval Systems Engineering of the Naval Sea Systems Command. In May 2025, he assumed command of the Naval Surface and Undersea Warfare Centers and continues to serve in both roles. Admiral Small, thank you for joining me on the podcast, sir. I look forward to this discussion.
Thanks for having me, Steve. I'm really excited as well. I look forward to a great dialogue here.
Admiral, you've been involved over many years in all phases of submarine design and construction. What are the biggest engineering challenges you've seen evolve over that time, especially from your early career until now?
Yeah, thanks. That's a great question. And I'm going to dial the answer out a little bit to incorporate both warship and submarine design because like currently in my role as the chief engineer, that's my purview and it all runs together and I have good insight into all of it. So there's certainly plenty of detailed engineering topics to choose from in terms of specific challenges. Again, I'm going to dial it out a little bit and talk at a very high level. I think overarching challenge that I've seen across my career, which has now spanned over 30 years, is the frequency and quantity by which we're doing clean sheet warship design. And the bottom line is we're not doing enough of it. And I think that's a root cause that leads into another, a kind of cascading set of issues that kind of ripple through in a number of ways. Certainly, there's a force architecture and force size aspect of this. How many ships do we need in the fleet? Of what type of ships do we need? And that dialogue would drive the discussion of, well, when are we doing new warship designs and the frequency by which we do that? I'm going to kind of table that for now and talk, from a fleet architecture perspective. There's another piece of it that talks to technology development and investment in R&D and design work, non-recurring engineering to design those ships, but also having the technology and systems to incorporate into those warships. I hope to get back to that in future opportunities in this podcast a little bit more. But I do really want to focus a lot of the dialogue here with ASNE, and again, in my role as chief engineer and commander of the warfare centers, on the people, the engineering competency that we tend, that's how we talk about it, the engineering competency, but it really means the sum total of all of the engineers and naval architects who are working both from a government perspective and an industry perspective on the esoteric, warship design. And so when we don't do enough clean sheet warship design and cycle those folks and those engineering competencies, we don't build the depth and experience that we need across the design industrial base to be as responsive as we'd like to be when it comes time for new warship designs. And there's a bunch of factors that play into this, but one of them is low demand for commercial ships, obviously, in our nation has contributed to the fact that there's really just not a big commercial demand for naval architects and naval engineers. And as a result of that, the pipeline of development in academia has gotten smaller. There's fewer curricula out there and fewer students in those curricula and fewer professors teaching those curricula. And then there's also what we've had in really the peace dividend since the fall of my career, and I talked about this in my ASNE speech at TSS a couple months ago. My career started in 1995, over 30 years ago now, really just after the Berlin Wall. I remember the Berlin Wall coming down while I was a freshman in college. And but in that time period, again, the fleet size has gone down. We've done less shipbuilding and designing, and we've had long production runs of very successful warships now with the Arleigh Burke class DDG-51 with 3 flights and going, and the Virginia class submarine that was designed in the post-Cold War era after the cancellation of the Seawolf program. And again, that's a very successful program. We've modified the design in various blocks, and we continue to build them. But what that has also contributed to is, a relatively small amount of clean sheet warship design. And warships are the most capable, but also the most complex and challenging systems that really exercise the full spectrum of warship engineering competencies, across the board, from hull design and performance to all the combat systems and electrical power generation, propulsion. They really exercise all of those muscles, and those long runs with relatively small upgrades along the way tend to reduce the demand for that engineering expertise. So all of those things have contributed to the point where we are today, where we want to increase the size of the fleet. There's been long runs of these warships, and a lot of the folks who are experienced in doing those designs have retired. Many of them are still in the gray beard or gray hair status, and we call upon their expertise to help us out. But for the most part, the people in the workforce, and I tend to include myself a little bit in this, because it's not like I've had the opportunity. I've had really an amazing opportunity, been involved with the start of 2 submarine designs in my 30-year career, but I kind of nailed the timing, and I nailed the opportunity to get into those programs. And so we've got relatively few people who have real kind of stem to stern, from design all the way through detailed design, production of these warships. And so we need to get after that. And that's kind of the problem statement. I'm going to come back, I think, in future questions and dialogues about what the opportunity is and what we're doing about some of those things. Because, that, again, this answer is the problem statement. The next answer coming up is some of the great opportunities that is going on right now, and some of the things that we're actively doing to get after that and build up our muscles, as in the analogy I've been using about experience and expertise and just capacity in the design engineering workforce.
As someone who helped stand up the new attack submarine program, SSNX, how do you approach balancing innovation with reliability, and maintainability in submarine design?
Yeah, that's a great question. Again, I mentioned I nailed it. I had this great opportunity. So my early in my engineering duty officer career, I had the great fortune to get in at the very beginning of the Columbia class submarine design program, and then stayed around long enough, and again had the opportunity to stand up the SSNX design program. So that's been really just I love submarine design, and I'm probably come back to that as well. So, but certainly it's a balance in any new program, whether it's a ship or a submarine, about how much technology to put in. And, you know, from a risk perspective, and any new warship design program is big and complex, and has a variety of risk. And we tend to like low risk approaches if you're a program manager, to make sure that I'm going to meet my cost, schedule, and performance goals. And that argument, which is very sound and very well documented about, programs who have struggled with that in the past, would tend to reduce the amount of technology. Technology insertion then somewhat equals risk. So that's kind of one aspect of it. But from another aspect of it, if you don't have enough technology, the whole point of having a new warship, going back to my last discussion, is that you need a new capability. There's something you need that you don't have, and that's driving you to add capability and generally technology. Also, going back to something I mentioned but really didn't detail in the previous response, was the relationship between these new programs and the R&D funding to develop the technology. And again, prior to the Cold War era, we were more organized in a way such the engineers like myself and the organizations that we did were also the technology developers, and had budgets, and in the Cold War era and before that, there was so much work going on that there was always kind of a good, robust pool of technology development across the board, and we could stand up programs as needed out of that. Now, since the peace dividend and over the decades, we've gotten to the point where we don't really get the funding and the opportunity to do that technology development until we get the big new programs and their requirements set such that the technology development becomes part of the ship acquisition program. And that could tend to make those programs, again, more complex. So it's really fine balance between having enough capability and technology in the program to justify the program and meet the capability needs that have been identified for this new warship, but not putting so much in that it just gets too risky. And there's great examples on both fronts. There's recent examples like the Ford aircraft carrier program and DDG 1000 are cited as programs that have had too much technology insertion in one program. But then I'll just say another a struggle, and maybe something I'll get back to, is we've been trying to get a DDG-X program off the ground recently to replace the DDG 51, and that has so far been a low risk approach, meaning we need to reset the margins, have a new hull form, give ourselves room to grow, but we're going to carry forward legacy technologies. And that is a low risk, program of record technologies, and that's a low risk approach. But the flip side of that low risk approach is it basically is a bigger ship that has the same warfighting capability as a DDG 51. So it programmatically can get challenging to launch. So long answer, but getting to the real answer to the question is the ideal state is where technology gets you both capability and sustainability and those other things that you would like. And one particular aspect, going back to the SSNX example, that I'm bullish on is really the sensors and the structures of the submarine. The structures of the submarine is what gives us kind of some of the most challenge over the life cycle of the hull, or life cycle of the class, is understanding the status of the structure and maintaining the status of the structure over a 30 to 40 year time frame of the class of warship even. And then from a sensor and performance perspective, we're trending towards, just more and more sensors, strapped in and on and the outside of the hull. The more sensors, the more capability, the more acoustic advantage we have and capability advantage we have over submarine. And we've seen this progression over the history of our submarine designs, which again is near and dear to my heart. But recently we've gone from just having like bow sonar arrays to bow sonar arrays and wide aperture array panels down the side. And now we're adding large vertical arrays in concert with the wide aperture arrays. And I joked as a program manager for SSNX, if we could just build the submarine out of sensors, then it would be fantastic, because we're always struggling to integrate the sensors on the outside and deconflict all of the conflicting areas. But I think that's kind of a joke, but there's some aspect of like technology, that might be closer to reality than we might think. And to some extent, if we can make the structure self-aware, is really this ideal technical state where the structure is telling us what its health and is, such that we can spend less time inspecting it in maintenance availabilities and then doing, finite element analysis to make a risk assessment approach of how safe and what is the status of that. If the structure can tell us how healthy it is, that would be a game changer. And then also, if the structure could tell us, what's going on around the submarine in terms of like being a giant sensor for all the other emissions and things going on outside the submarine, that would be a game changer from a capability. So again, that sounds a little bit far-fetched, but I think there's something there, and that is exciting for me. The last piece I'll talk about this one is really digital engineering. Digital engineering is something we often talk about and we use and live. And from a submarine design perspective, the Virginia class was noteworthy in its design in the 1990s, because it was the first submarine design that was done with 3D CAD technology, and that has translated into modular construction, which has been a game changer from a construction perspective. So it has definitely moved the needle forward from a construction perspective. It's not all good. There are hard lessons learned. We're going through some of those on Columbia, with just maintaining and updating those digital tools and how that translates into production. It's not always a slam dunk. But also the translation into sustainment is where we need to get better with digital engineering. We understand what the trade space is for designing and building that from a digital engineering perspective. We really need to continue to flow that digital thread down through the life cycle and sustainment, which is done by different organizations and has different aspects of it. And so I think digital engineering and continuing our learning and improving the way we execute digital engineering throughout the life cycle is technology that is gonna really have a big impact on improving our sustainment outcomes. So I think there's definitely something there.
Sir, in your experience overseeing submarine construction and repair at major shipyards, what are the most significant practical constraints that influence design decisions?
Yeah, this is is a great question, and again, I've had the fortune to have two tours as supervisors of shipbuildings for both our submarine shipbuilders, and now, as in my role as O5, get much more insight and experience into the public naval shipyards who are doing the sustainment work. And I get involved on the surface ship side as well. But I think this is somewhat tied to the previous conversation about modular construction. And again, we talk about how 3D product model CAD has enabled modular construction, and that has been a game changer from a Virginia class construction perspective. That said, it has also driven in, since we're now building up big modules, the interior of the modules is built up completely separate from the hull. And then we slide that module into the hull, and then we bolt the big hull modules together, weld them together, I should say. And all of the things on the inside, the pipes and the systems, have to line up such that we can pull them across those hull seams and hook everything up. That's kind of how it works. But that means there has to be a level of precision that's in the engineering design to make that line up with I'll say a minimal amount of work at the deck plate to change and have tradespeople making adjustments to make that all work. So that drives a level of precision into the design articles that can be a hindrance both that just means you have to build it to tighter tolerances, and that means you're going to maintain it at those tolerances throughout the life cycle of ship. So there's a payback of that precisions. The other and then, so now we've built it modularly, but then we ship it to our naval shipyards to sustain it and, throughout its life cycle. And we don't have the luxury of cutting those seams open and pulling the modules out later on when we're doing that sustainment. So there are challenges in sustainment with access that are sometimes made more difficult by what has been the optimization. There's something called the 138 rule we use in submarine shipbuilding. It means if it takes you 1 hour kind of in the workshop level, once you put it on a module, it's going to take you 3 hours. And once you put it in the hull, it's going to take you 8 hours. So that tends to force everything all the work as far upstream as possible. But now when you're in a public naval shipyard and the ship is all pulled together, you're already in the 8 regime all the time, the 8 hours regime, the hardest regime. And so that can be a challenge to deal with. So to the extent, we've been focused on that for a long time and continue to look at how to make that balance between modular construction and sustainment activities. And then I'll just want to mention another phenomenon that our current demand signal for shipbuilding is driving, which is called distributed shipbuilding, is how we call it. And to some extent, the Virginia class program was set up from like this in the beginning, in that we have 2 fabrication places, which is Newport News Shipbuilding and Electric Boat's Quonset Point facility in Rhode Island, doing the fabrication pieces. And then we have 2 facilities that do the assembly and delivery. And one of those is also Newport News Shipbuilding, but then the other one is Electric Boats facility in Groton, Connecticut, that does final assembly and tests. So we've got that at a micro scale, but now as we struggle and need more submarines, that's flowing down where the submarine shipbuilders are using more vendors to do that modular construction. We're getting those pieces from more places. That's extending down to the Gulf Coast and places like Austell, and Newport News Shipbuilding has a new Charleston operations site that's going to be building up those modules. So basically, there's going to be more people building those modules and shipping them to some waterfront assembly and test location. And that means that now more different vendors are going to be building modules to the same design and the same design deliverables, whether that's paper or electronic. And those manufacturing tolerances need to be adopted by that entire supply chain, such that it all comes together and works together. So it's something that we need to continue to work on, the balance between having enough precision in the design such that we can exercise things like modular construction and distributed shipbuilding, but can't be so onerous that those places, need to go back. If you need to go back to the source of engineering or the design engineers to solve a problem, that can slow the process down. And as we get more distributed in our shipbuilding, that has the potential really to become a problem. So we've got to figure out, from a tolerances, engineering, design, and digital engineering perspective, how to get enough information into the product model and design deliverable such that people can build it, but still have tolerance and allowances for the shipbuilder to deal with, day-to-day issues that they might run into in manufacturing.
Admiral, what are some common or interesting misconceptions you've come across regarding naval design during your time teaching submarine and ship design at MIT, and how would you address them?
Yeah, thanks for asking that. And the first thing, again, in this example, I'm going to dial out the answer just a little bit, but the first thing I'll mention with respect to MIT is, first of all, warship design is an esoteric field, and submarine design is like super esoteric, because it's like even more esoteric than surface ship warships. And to the earlier point, we don't have a commercial demand so much, in the United States Navy, but from a warship design perspective, that is inherently a governmental thing. And so there's not a lot of places you can go to and learn how to design a warship. And so the MIT curriculum, which is called the Naval Construction and Engineering Curriculum, it's a graduate level curriculum in warship design, was established back at the turn of the previous century, into the 19th century. We used to send our naval architects to England to learn how to do naval architecture. And we're friendly with them now, but we weren't always as friendly with them, back in the day. And at some point they decided to stop taking us, and we had to develop our own curriculum. So now, over 125 years ago, we developed this curriculum at MIT to teach warship engineering, and it endures and thrives. And I've had the good fortune to both graduate from that curriculum and go back and teach in it. So, but it is esoteric, and talking about those, getting the bespoke sensors and radars and missile systems and survivability features to all work out in warship is not at all a commercial endeavor. And it takes people with experience and expertise in doing that to teach it. So, I know certainly having to go back and teach topside integration as a submarine designer in that course was a challenge for me, because again, that is an esoteric field. One of the challenges I see now as O5 is that the two trains of surface warship design and submarine warship design tend not to intersect too much. They have their own groups of people that do it in various locations and expertise. And again, in O5, seeing across those, I get frustrated sometimes because I see design problems or design solutions or collaboration that occur across surface warship designers and submarine warship designers. And so I'm constantly pushing that to make sure my own staff and the people doing that work are taking the experience and best practices from each other, such that we get the best results possible and we have the full data set and experience set as possible. Again, going back to my first kind of answer about we need to really exercise and flex our muscles from a design perspective. There are relevant lessons to be learned, whether you're designing a surface warship even though they're esoteric and have different solutions, naval architecture is naval architecture, and propulsion, there's a lot of fundamentals that cross. And so I'm constantly trying to make sure that those groups are talking to each other and sharing their experiences. I do want to pivot and get more into the misconceptions piece a little bit. And again, raising it up, not so much about MIT and surface and submarine design, is this concept of the specifications and standards, and specifically military specifications and standards. We have those. I could go into a long, rich history and discussion about this topic, but certainly as NAVCO5 and the engineering outfit of the NAVC Syscom, our charter, one of the things we do is maintain the military specs and standards for warships, and that includes over 3,000 specification standards, technical publications, and things like that. That's our job, to steward those things forward. They tend to be cited as the source of the problem in many cases, where designs can become too complex or too hard or too onerous to build. And so that is a challenge. By policy, NAVC and the Navy only maintains and uses military specifications where there isn't an equivalent commercial specification. So part of the job of stewarding those specifications and being, maintaining them up to date is constantly being aware of what is out there in the commercial specifications space from surface ships. And there's not really an equivalent, there's no such thing as a commercial submarine spec that we would, so submarines, inherently tend towards having to have a military spec because there's just no commercial equivalent. So by policy, we only have those military specs where we need them. So there's a misconception that they're onerous and they're hard to do. And so because of that, we'll just try to use commercial specs as much we can in doing these warships. And whether they're capital warships, destroyers or unmanned systems, there's a tendency to think, well, mil specs are hard and onerous, so we'll just use commercial specs and we'll be able to go quicker and get a better outcome. And there's logic, and to some extent that's true where it works. But at the same time, the warships, whether again unmanned, manned, big, small, are being developed to meet a military mission. And the military missions generally involve, carrying people and the manned, which is hard, or not carrying people, which is also hard for a different set of reasons, and carrying bespoke combat systems, radars, computer systems, networking systems, crypto that's required, communications equipment, and then weapon systems that include ordnance, warheads, guns, missiles. Um, and then there's a survivability aspect. We want our warships to be survivable. And that means doing different structural designs and watertight and firefighting and recoverability and susceptibility, signatures reduction and things like that. So I'm not trying to defend military specs, for the military specs state. I'm trying to highlight the fact that we have them because we need our warships to do military missions. We send them into the fight. We need them to fight. They're designed to take a hit, and they're designed to keep fighting. And there's not really an analogous commercial spec. And if we really defaulted to purely commercial specs, they would be a poor warship. They would not be effective. Those combat systems and bespoke things wouldn't necessarily work together or as we want them to, and they wouldn't be survivable in the ship. So, that's my job, is to help the acquisition organizations find the right mix of standards to meet their mission requirements. And that takes dialogue and work, and that's our job to do. But I'll just kind of wrap this up by saying, well, first, I want to point out before I wrap up that, a lot of these warship classes that are very successful today go through this kind of journey, and it's a decades-long journey. To design and field and get into the heart of a warship program takes 20-ish years, and most of those warships don't come out with no problems at the front. They take some teething problems to get through how to build them efficiently and get them all to operate correctly. And there's plenty of examples of that for some of the most numerous and most successful warships that we have in our fleet today have gone through this journey. 688 class Los Angeles class submarines are a great example. They're, if you go back and read the early parts of that class, it was a very checkered start, but turned into just an incredible platform that we built over 60 of them, and they've been the workhorse of the fleet for a long time. DDG 51 has some of that. LPD 17 certainly went through that journey. So it's not easy. They're not easy to deal with and maintain, but they're what really kind of drive the capability and the longevity that some of our ship classes have. So finally, on that note, it's really my job as the steward of those specs and standards to do everything that I can to make sure they're up to date and modern, and they're not onerous, and they incorporate new manufacturing techniques and new technologies and new products that the industrial base is putting out. And so we need to, work hard, and we're doing that, and we're doing more of that with the maritime industrial base, which is great collaboration. But it's also our job to make them easy to digest. And I mentioned digital engineering already in this concept, but we're working hard to make sure that those specs and standards, which again are derived from decades of experience, and we think there's real value in them, but they need to be up to date and delivered in a digitally native format such that they can be ingested into the design tools and then flowed down to the manufacturing industrial base. Again, we're talking about a bigger and more layered and nuanced industrial base with distributed shipbuilding. So we need to do everything we can to make sure that those bespoke military standards that are invoked because we need them to be can be ingested into the design, flowed down to the vendor base, and understood, and not be a burden, or more of a burden than they absolutely need to be to the folks who are developing and delivering those things. So we're thinking hard and working a lot about how to make that go as best we can.
Admiral, the role of Chief Engineer and Deputy Commander for Naval Systems Engineering at Naval Sea Systems Command gives you a broad engineering oversight. How do you prioritize among the competing demands for performance, cost, schedule, and technical risk when you're managing multiple programs?
Yeah, thanks. That's great. And I love this job. I really have two great jobs right now: the chief engineer job and the commander of the warfare centers. Gives me just incredible insight and oversight of the entirety of our naval engineering competency that I mentioned before, but really get involved in all of the NAVC Syscom ship acquisition and systems acquisition programs. So it's really a fantastic job. And I'll warm up into this to say, what is that scope? The Naval Sea Systems Command has, Admiral Downey and Mr. Miller, our leadership, have they published a strategy or strategic plan, early on, and that involves really 5 lines of effort, and they're aligned to the Navy's lines of effort. But really, I'm not going to go through that whole spiel, but the first two, LOE1 is accelerate force generation. So, broadly speaking, we need to do exactly that. Force generation means designing and building and delivering the warships and the systems and the ordnance that we need to meet the national needs. So we got to, really get better at building everything and delivering it. LOE2 is about generating readiness, which means making sure all of that new stuff that we've delivered and all of the stuff that's in the inventory already, that's in the fleet, is sustained and ready to fight and available. And so that's a big effort too, and involves all the sustainment and maintenance and modernization activities. So just an incredible scope of work that I'm describing that I'm involved in. There are LOEs 3 through 5 that also talk about digital engineering. I mentioned the people. I'm constantly talking about an infrastructure, so I won't go into those in as much detail. But basically, my task as the chief engineer and lead of the engineering competency is really to develop and apply the talent and experience and innovation across that ecosystem of force generation and readiness, force generation and readiness generation. And it's a fantastic job. I love it. And there's really no better time to be a naval engineer, quite honestly. And this is the opportunity statement. I talked about the problem statement, I'll say, where we don't do enough warship design early in the podcast. And now this is where I'll talk a little bit about the opportunity. But obviously, there's a resurgence of national interest into regrowing the size of our fleet to meet the needs of our nation. We just had a new national security strategy and national defense strategy have been published. And so we're seeing where those priorities are, and kind of throughout, certainly as long as I've been in the Navy, we've been talking about the need for a larger Navy. And we're working hard to kind of not lose end strength at this point, but we're now trying to get back and increase the size of the fleet. And so there's this revitalized national interest, and you can see the evidence of that all over the place. There's executive orders, there's draft legislation about Ships Act, and most recently, the Secretary of the Navy and the President have announced the Golden Fleet effort, which again is new platforms like a new frigate program and a battleship program, but also encompasses the rest of the fleet that we have, and rounding out that fleet of warships with combat logistics force ships, unmanned forces, hedge forces that the CNO talks about. So that Golden Fleet kind of really pertains to all of that stuff. So there's a lot of opportunity now, and we want more of those things. So from an engineering and design perspective and competing demands perspective, we have to develop the talent required to do all of this work, and then deploy that across all of these new programs and existing programs. And so that's a combined reliance on the expertise of both our military and our industry partners. When I talk about this, I'm really not talking about just the military aspect of that is mostly in, again, O5 headquarters, and the warfare centers is where much of our engineering design capacity is. But all of our industry partners are going to need the capacity and the experience to execute all of this work as these efforts mature and grow. It's really a national call to action, and we need to redevelop the vocations of both shipbuilding and tradespeople. We've heard a lot about that in recent year with the maritime industrial base. What I'm excited about is we're really moving that forward into not just tradespeople who are actually building the ships, but the engineers and designers who are required to do the support of that construction, but also the upstream development and fourth generation design piece of that. And so there are some tactical things that we're doing with help of the maritime industrial base, specifically with respect to revitalizing curricula. And so one thing in particular that is exciting to announce is in combination with the maritime industrial base, we in NAVCO5 have revitalized something called the NAVC Professors Program. And we are now funding the professors in 9 universities that have relevant naval architecture and ocean engineering curricula. And we're also working on making sure we develop that curricula and expand that curricula across really the full spectrum of academic opportunity for naval architecture and engineering in the United States. And by funding the professors, that we can then increase the throughput of those curricula, because the demand signal is coming. And again, that demand signal is going to be both in the government and the industry side. So we're trying to get ahead of that, or certainly stay up with it as much as we can by developing the talent pipelines for engineers and designers to respond to this demand signal for engineering talent. But it's really a great opportunity, a great time, and that's why we're excited to talk to folks like ASNE, and certainly collaborating a lot with them, but other professional organizations like the Society of Naval Architects and Marine Engineers, American Bureau of Standards, again, just like industry and engineering advocacy organizations across the spectrum. We're really trying to partner with and work on this national call to action.
Sir, given rapid advances in material science, propulsion, automation, and sensor technologies, which emerging technologies are you most excited about integrating into future submarine or undersea warfare systems, and why?
Yeah, great. I already mentioned one, which is this kind of North Star I have of building the submarine structure out of sensors. Like that's a great one that I love, and I think there's something there. But I do want to talk about some other things we're doing. Additive manufacturing and advanced manufacturing. A lot of the technology that we need to adopt. There's technology for performance, and those are things like sensors that I talked about, or missiles and radars and things like that. But there's also a lot of technology for manufacturing that we need to really adopt, and we've been really focused on that. And again, our partnership in NAVCO5 with the Maritime Industrial Base has really jump-started and accelerated a lot of those efforts. One of which, again, not the only one of these advanced manufacturing techniques that I'll talk about and we're most mature in some of our efforts on is additive manufacturing. And so that's certainly been in the, people have been frustrated with additive manufacturing for a long time. Like, why don't we just have that everywhere? Like, why is it taking so long? And back to the comment earlier about what's a common misconception. I don't know if it's a misconception, but again, in the same vein as the military standards that I talked about earlier, there really is not a commercial equivalent of additive manufacturing for the warship things and the piece parts that we need to really accelerate the design and build of warships, but also the sustainment of warships. There's really not a military or not a commercial equivalent of additive manufacturing in support of that. There's certainly a lot of additive manufacturing in the aircraft industry, and there's a lot of work going on to leverage that from commercial aircraft into military aircraft. So what we're doing in NAVCO5 and the MIB and naval reactors, importantly, is we are doing the work. We are creating standards for metal additive manufacturing in support of warship design and sustainment. Again, those standards don't exist, and we're creating them. We are doing the fundamental research and development work funded by the MIB. Remember I talked about we generally don't have R&D funding to have the technology ready to go. This is another example, but the MIB has opened up the opportunity with the funding to be able to fund that the fundamental R&D. So O5 is overseeing the work and creating the standards for metal additive manufacturing. We're also doing it in a way that involves the industrial base and the vendor base, such that we have OTA contracts and funding from the MIB and vendor base involved, such that we are doing the R&D for the metal alloys, which are, copper, nickel, aluminum, bronze, big, heavy. The pieces we need are measured in the hundreds, tens or hundreds of pounds, sometimes even thousands of pounds. These are big, what would replace a legacy casting or a forging. We're now going to build out of additive manufacturing. And so we're developing 11 new material process combinations. Little esoteric term, but again, it depends on the alloy and it depends on the technology that you use to do the additive manufacturing. There's a couple different technologies. There's directed energy deposition, or kind of like wire feed, putting it down. There's laser powder bed fusion, like building it up out of a powder. So there's different additive technologies. There's different metal alloys. We're creating the standards for those such that a vendor can buy a part that has either a legacy casting, a legacy forging, or now a metal additive manufactured part that's part of that valve body or whatever that component is. And that's really going to help us unlock capacity in the supply chain and really relieve some of the roadblocks to building submarines, but also for the obsolete and esoteric parts that we have on our aging fleet that's not in production anymore, will allow us to build, small production runs of parts that aren't in fabrication. You can't buy them anymore, but we can now print them. So that's a technology that's really going to move the needle, and we're years into that now, and we're publishing those standards such that they're now becoming available to the people to purchase them from. We're working with the shipbuilders to get those part numbers in their inventory. We're working with NAVSUP and DLA to make sure that they can procure those parts from these vendors that we're helping to develop. So that's a big one. There are other things in that genre, like of advanced manufacturing technologies, plasma spray and robotics and things like that. And so there's efforts going on there too, but in the interest of time, I won't mention those. Another technology that is going to be super important, though, is AI for design tools. I talked earlier at length about, building the muscles and the people and with experience and expertise to do these esoteric warship designs. Part of our way out of that relative lack of experience and depth is going to be by, we're going to develop people with curricula and legacy fundamentals, and we're going to develop smart, intelligent design tools. And the combination of those two things, humans with degrees in the fundamentals and intelligent design tools that can help us get through the experience and expertise piece of it, is really going to unlock what will allow us to do designs quicker and also designs better. And so I think that's a really exciting field. Submarine concept design and warship concept design has always taken a long time. It's the fundamentals count. We're not going to, automate the fundamentals, and humans will always be in the loop. But just like any other application of AI, we're going to be able to do it quicker and perhaps better by having intelligent design tools at our side. Just like you can write a letter or do some administration easier with your AI tool, you're going to be able to design a warship better and quicker with an AI design tool. So I think that covers a lot of the exciting stuff I'm looking at.
Admiral, as someone who has seen both, from the dock to the deck plate, life cycle and academic design teaching side of naval engineering, how important is hands-on shop or yard experience for naval engineers beyond that theoretical work?
Yeah, that's a great question. And I've talked at length in this podcast how warship design doesn't have a commercial equivalent and is esoteric in nature. So I do think that there is a healthy dose of deck plate experience that is required for any really experienced naval architect or naval engineering. So there has to be a collaborative approach to academic learning and the fundamentals at curricula around the country, like those NAVC professors programs that I've talked about and MIT. But then there needs to be a complementary time frame of experience to be on the deck plate somewhere. And again, I've had that, and as an engineering duty officer, that's kind of our model. We take officers who early in their career are operators of surface ships and submarines. We send them to formal academic curricula like the one at MIT, and then we send them either just prior to or just after that academic time to a waterfront qualification tour where they're at a supervisor of shipbuilding, a regional maintenance center, or a naval shipyard to put hands on and apply the fundamentals and the operational experience that they have in the medium. And you've really got to, so that's kind of our model that we develop engineering duty officers with. And that works well for us, and we'll continue to do that. I think in industry and other applications that aren't, active duty military or engineering duty officers, there does need to be some of that mix of the fundamentals, the waterfront experience, and then the real hard part is it's very difficult for those who are not active duty in the military to get the operational experience. So that's why it's always going to require a blend of operators and active duty military and government civilians and industry civilians to get the job done. And that team has to be working tightly together. But all of them need to have some exposure to the deck plate such that you can really see it in application. And it just, there's no replacement for seeing the complexity of the integration and the tightness of the spaces and how the systems of systems have to come together. And so in industry, that can be at the facilities where these ships and submarines are being built. But in government, that can be at a whole host of waterfront activities. We have supervisors of shipbuilding who are overseeing the new construction of ships and submarines. We have regional maintenance centers around the world that are doing the maintenance and sustainment of primarily our surface ship fleet. We have naval shipyards in the United States and that are sustaining our nuclear powered warships. And then as we get into more modular shipbuilding, again, we're going to have, I'll say, waterfront sites that are building the piece parts of the submarine. It's going to be important for someone at that facility to know how it's all going to come together such that those, you have that level of feedback at a modular, I'll say a distributed shipbuilder who's just building a module is pretty far removed from how that module needs to come together with the rest of the ship and what the intent is. And so there's been a big press by the Navy and the Maritime Industrial Base to get out to those vendors. And those visits are always great when someone in uniform goes and really explain, well, hey, the stuff that you're building is super important. People's lives depend on it. And this is the kind of stuff it's going to be used for. And it's always eye-opening. There's always people in that crowd who's like, wow, I never knew that, or I never thought about it like that. So it's really important to develop our engineering competency with rotations to the waterfront and kind of cross-organizational experience to get that, because it's kind of required. It's hard to really design a good warship if you haven't seen how it's all going to come together. And to the extent you can get a ride or underway on one of these amazing vessels would really help you in your career as well. So it's an important mix. We need to continue to work to develop that.
With submarine designs evolving over time, how do you see modularity, upgradability, and future proofing being incorporated into new builds to allow emergence of new technologies over decades?
Okay, hey, that's a great question. And the Virginia class submarine is a great example of this. But there's always this fundamental question at the start of any new warship design. How much margin do you need to insert into that design such that it can be evolved and adapted over time to add capabilities and to evolve to different mission sets. And so that's kind of that's fundamental work, and always is a challenge because margin means you're making the ship bigger at the beginning, or whether that's in size or what we call kg margin, which is the ability to manage the center of gravity of the ship, to add capability over time. And that basically makes the ship a little bit bigger and a little bit more expensive, but you need to make that investment up front such that you can have a nice 30, and in some cases, a lot of cases actually 40-year lifespan of these warships. The Virginia class submarine is a great example of that. We've evolved the design over numerous blocks over decades now, and certainly the more recent examples, some of the changes have been smaller earlier on, but the most recent, the submarines we're building right now are like 84 feet longer and have this vertical payload tube module inserted in that, which gives them a ton of capacity from vertical launch perspective. And then, we're adapting that even further over time to add capabilities associated with those vertical payloads and large ocean interfaces. And we did not make the ballast tanks on the ends bigger. We really cut the submarine in half and inserted this module, and only because we had design margins built in from the beginning are we able to do that without having to change the rest of the submarine to support that. So that's key and fundamental, and we're certainly exercising that over Virginia, and we'll continue to do that because we'll eventually have built enough Virginia payload module submarines, and we'll need to get back to building smaller attack submarines that don't have that, because we just don't need that, and we need submarines to do different missions. So we'll continue to evolve the submarine, and then we need SSNX. Virginia class submarine was laid down in the post-Cold War era. It was designed to be in support of littoral operations or near-shore operations, which was a focus of that post-Cold War 90s era, forward from the sea and everything, again, right when I was joining the Navy. And again, it's been a workhorse for us, but the threat has evolved significantly since that time. And now we have this tall China threat and the resurgence of Russian submarines, which really kind of never went away. They're building very capable submarines, and the Virginia class design is limited in its ability to be modified to adapt completely to those new threat missions. And that's why we need SSNX. And so SSNX needs more horizontal payload capacity, and it needs speed, and it needs stealth, just like any good submarine needs. And but also with unmanned systems, and the incorporation of unmanned systems is a hugely challenging task. And so a lot of the work that we were doing early on and continue to do in SSNX is how to integrate unmanned systems into this future platform. And vertical payload tubes are good for missiles. It's harder when you want to put a UUV in there, because you got to somehow get it out and turn it over or have it swim out vertically. So we need more horizontal payload capacity for SSNX, and we might want different or larger ocean interfaces for things other than ADCAP torpedoes that we might be deploying from that submarine. So that has been a big focus of the early trade space exploration that we were doing on SSNX, and will continue to be part of the, because it's disruptive to put any large ocean interface in. Again, the submarine got a lot bigger to put in that vertical payload tube module, and to the extent we want to incorporate large horizontal ocean interfaces, to some extent that's harder than incorporating vertical ones into the submarine design. And so there's trade-offs that have to be made to put those large ocean interfaces in. So that's the balance that we're going to be working for SSNX. How much horizontal payload, what are the interfaces, what does that do to the rest of the design with respect to size and complexity and cost? But that is the future proofing of that design for SSNX, and any design is going to be the overall margins that we put into the submarine, and then where do we see the potential to upgrade and add capability over time. Again, we may not want to put all of that capability in the initial block of the submarine or the first release, but we might want to have preserved the opportunity to make more design changes later on. And you got to have some idea of how that's going to go when you do the original design. So that's really exciting work. Again, I love submarine design. It's the most over-constrained system of systems I can imagine. And I think that's why it's so fascinating to me.
Admiral, will you share some of your thoughts with us about unmanned systems?
Yeah, thanks. And this is near and dear to my heart. As you heard in the talk up, that I spent almost 4 years as a program manager of unmanned maritime systems not that long ago, and it was in 2018 to 22 timeframe. And ask anyone in the unmanned systems world, it's like a roller coaster. There's ups and downs. And I got that from people when I first joined on, and it was exciting. But I'll say that the era that I was in was kind of an up, and it was exciting, and the budgets were going up, and we were trying a lot of new things, and we had new authorities from Congress to try to go faster. And so it was an exciting time. And but that said, integrating a fundamentally different technology like unmanned systems into the big Navy is a very challenging task. And my boss, when I was a program manager back at the time, my boss was Admiral Casey Moten in PEO USC, and we had a lot of good fundamental engineering discussions about what was how we should go about this, and what was the task, and what were the strategy we should use. And we often compared it, and he often compares it to the incorporation of naval aviation into the fleet. That didn't happen overnight. It took a period of decades. There was a lot of trial and error and a lot of learning that occurred before we honed in on what is the modern aircraft carrier and air wing that is so capable today. And so I feel that we're in that kind of decades long transition period, and everyone wants to figure it out exactly, kind of discreetly, and it's going to take multiple trial and errors. It's going to take time and integration and experience and experimentation, and we're in that process now. So there are still ups and downs, and we're going through another transition right now with our acquisition reform efforts. And there's Rapid Capabilities Office being stood up, and an organization solely focused on unmanned systems. And so we're still iterating on the organizational constructs to field and scale unmanned systems. We're having success to some degree with scaling smaller unmanned systems. So again, we're not making progress. And then the other kind of aspect I'll talk about it is back to the military specs and versus commercial specs for unmanned systems. Again, unmanned systems are intended to be relatively cheaper and smaller than our manned systems, because we want to scale them. These are the hedge forces that the CNO talks about. This is our opportunity, is to use unmanned systems to be part of that hedge force. And if you talk about scaling and upsizing the fleet quickly, it's going to be hard for us to quickly increase the number of capital warships like destroyers or submarines that we're going to have, but we're going to be able to more quickly scale the size of the fleet with smaller hedge forces and unmanned systems. So we want to build a lot of them. But I would argue, again, there's really no commercial standard for an unmanned system. Again, my experience was we really only want these unmanned systems for military missions. And so we tend to say we want to scale them quickly and use commercial standards. And then the next breath we say we needed to have really long range, be very reliable, carry a warhead, incorporate crypto, and integrate with our command and control systems. I'm like, okay, well, that's a tall task. And that is not a low risk engineering. Some of our higher end unmanned system programs and prototypes that we've been working with have been for very high end missions. And so, again, we're working across the scale now. We're back and scaling some smaller unmanned surface vessels for more targeted mission sets. We've seen great success of unmanned systems in the Ukraine war, and that's helped us, think about where we should go and moves we should make. So my only point here is that we're not going to figure it out exactly. Everyone is frustrated. I've had my own share of frustrating times with unmanned systems, but we're in the kind of decades long learning and adaptation period. And we're only going to get there through trial and error and learning. So I'm not adverse to different approaches. I'm not saying we only need to have, boutique high-end military specs for unmanned systems. I think we do need to try to build them as cheaply as we can, but we also need to figure out how to make them effective and reliable and integrated into our fleet. And those are not simple things and require detailed, there's some amount of standards required to do fleet integration and some amount of standards required to have a level of performance that you can rely on. And, when the first thing a fleet operator wants to know is this thing going to work for me? Is it going to, endanger me in some way in my warship that has all the people on it? And we need to be able to tell them, no, it's not going to endanger you. And yes, it's going to work as described. And there's some amount, there's a rigor and standards in engineering that's going to be required to deliver those answers. So we're working all the time in the learning of and experimentation with unmanned systems. I'm bullish on them. I love them at heart. They're near and dear to my heart, and I want to continue to support all of the efforts to figure it out.
Admiral, looking forward, giving your broad oversight at NAVSEA and Command of Warfare Center R&D capacity, what do you think are the biggest engineering or design gaps the Navy should focus on over the next 10 to 20 years to stay ahead technologically?
Yeah, thanks, Steve. I really already mentioned one from a design perspective. AI and intelligent design tools is really going to be an absolute requirement that we're going to need to stay ahead or even stay even technologically, because the rate of change of innovation and technology development has really picked up, and we're going to need to stay agile to be able to respond and adapt our warships, whether they be big manned capital assets or small unmanned systems. We're going to need to adapt them and evolve them quickly over time, and we're going to need intelligent design tools to help us do that. We also need to really kind of keep the R&D pool going, and I mentioned this a couple times throughout the podcast, but the stable and kind of fundamental developmental efforts for technology are, we need to have a ready locker of technology development going on. And some of the legacy structure of our acquisition system is boom or bust in R&D development with program efforts and these, what can be spaced out capital warship efforts, because that's where the big money is. And I think that's been part of our issue over the last decades in having technology ready to go and be quickly, kind of off the shelf and ready to put in at a TRL level of 6 and not have to require, a couple of decades of development to make it work. We need to think about how to keep the technology development going in an agile and sustainable way and not completely tied to the requirements associated with big capital asset platforms. And I think we're seeing some of that migration, and I'm optimistic. We're seeing modification of the acquisition system, or the requirement system has gone. We're changing how we do requirements. We're changing how we do acquisition organizations. I think we need to adapt the way we do technology development and investment of R&D funding in support of those things, because all of those changes are being with the thought of being more agile and responsive. And if we're going to be more agile and responsive from a technology perspective, we need to have a ready locker of technologies to go. And that means we need to have people working in that space in a sustainable way and in a way that's supportive, but not entirely driven by the big R acquisition program requirements. So I think that's some of the work that we need to figure out going forward.
Well, thank you, sir. Rear Admiral Peter Small, for taking time to discuss a broad number of naval engineering topics. I hope we can welcome you again back to Talk a Little, Learn a Lot, the podcast of the American Society of Naval Engineers.
Thanks, Steve. I had a great time. really appreciate the opportunity and look forward to doing it again.